In fluid dynamics, drag refers to forces acting opposite to the relative motion of any object moving with respect to a surrounding fluid. This can exist between two fluid layers or a fluid and a solid surface. Unlike other resistive forces, such as dry friction, which are nearly independent of velocity, drag forces depend on velocity. Drag forces always decrease fluid velocity relative to the solid object in the fluid's path. Examples of drag include the component of the net aerodynamic or hydrodynamic force acting opposite to the direction of movement of the solid object relative to the Earth as for cars, aircraft and boat hulls. Or acting in the same geographical direction of motion as the solid, as for sails attached to a downwind sailboat, or in intermediate directions on a sail depending on points of sail. In the case of viscous drag of fluid in a pipe, drag force on the immobile pipe decreases fluid velocity relative to the pipe. Types of drag are generally divided into the following categories: parasitic drag, consisting of form drag, skin friction, interference drag, lift-induced drag, and wave drag or wave resistance. The phrase parasitic drag is mainly used in aerodynamics, since for lifting wings drag is in general small compared to lift. For flow around bluff bodies, drag is most often dominating, and then the qualifier parasitic is meaningless. Form drag, skin friction and interference drag on bluff bodies are not coined as being elements of parasitic drag, but directly as elements of drag. Further, lift-induced drag is only relevant when wings or a lifting body are present, and is therefore usually discussed either in the aviation perspective of drag, or in the design of either semi-planing or planing hulls. Wave drag occurs when a solid object is moving through a fluid at or near the speed of sound in that fluid or in case there is a freely moving fluid surface with surface waves radiating from the object, for example from a ship. Drag depends on the properties of the fluid and on the size, shape, and speed of the object. One way to express this is by means of the drag equation, where Fd is the drag force, I is the density of the fluid, V is the speed of the object relative to the fluid, A is the cross-sectional area, and CD is the drag coefficient a dimensionless number. The drag coefficient depends on the shape of the object and on the Reynolds number, where d is some characteristic diameter or linear dimension and I1/2 is the kinematic viscosity of the fluid. At low Reynolds number, the drag coefficient is asymptotically proportional to the inverse of the Reynolds number, which means that the drag is proportional to the speed. At high Reynolds number, the drag coefficient is more or less constant. The graph to the right shows how the drag coefficient varies with Reynolds number for the case of a sphere. For high velocities, drag will vary as the square of velocity. Thus, the resultant power needed to overcome this drag will vary as the cube of velocity. The standard equation for drag is 1/2 the coefficient of drag multiplied by the fluid mass density, the cross-sectional area of the specified item, and the square of the velocity. Wind resistance is a layman's term for drag. Its use is often vague, and is usually used in a relative sense. Drag at high velocity. As mentioned, the drag equation with a constant drag coefficient gives the force experienced by an object moving through a fluid at relatively large velocity. This is also called quadratic drag. The equation is attributed to Lord Rayleigh, who originally used L2 in place of A. See derivation. The reference area A is often orthographic projection of the object on a plane perpendicular to the direction of motion for example for objects with a simple shape, such as a sphere, this is the cross-sectional area. Sometimes different reference areas are given for the same object, in which case a drag coefficient corresponding to each of these different areas must be given. In case of a wing, comparison of the drag to the lift force is easiest when the reference areas are the same, since then the ratio of drag to lift force is just the ratio of drag to lift coefficient. Therefore, the reference for a wing often is the planform area rather than the frontal area. For an object with a smooth surface, and non-fixed separation points like a sphere or circular cylinder the drag coefficient may vary with Reynolds number E, even up to very high values. For an object with well-defined fixed separation points, like a circular disk with its plane normal to the flow direction, the drag coefficient is constant for Re 3500. Further, the drag coefficient CD is, in general, a function of the orientation of the flow with respect to the object. Power: the power required to overcome the aerodynamic drag is given by. Note that the power needed to push an object through a fluid increases as the cube of the velocity. A car cruising on a highway at 50 mph may require only 10 horsepower to overcome air drag, but that same car at 100 mph requires 80 HP. With a doubling of speed, the drag quadruples per the formula. Exerting 4 times the force over a fixed distance produces 4 times as much work. At twice the speed, the work is done twice as fast. Since power is the rate of doing work, 4 times the work done in half the time requires 8 times the power. Velocity of a falling object. The velocity as a function of time for an object falling through a non-dense medium, and released at zero relative velocity v equals a0 at time t equals a0, is roughly given by a function involving a hyperbolic tangent. The hyperbolic tangent has a limit value of 1, for large time t. In other words, velocity asymptotically approaches a maximum value called the terminal velocity vt. For a potato-shaped object of average diameter d and of density iobj, terminal velocity is about. For objects of water-like density falling in air near the surface of the Earth at sea level, terminal velocity is roughly equal to, with d in meter and vt in ms. For example, for a human body 70 ams, for a small animal like a cat 40 ams, for a small bird 20 ams, for an insect 9 ams, and so on. Terminal velocity for very small objects at low Reynolds numbers is determined by Stokes' law. Terminal velocity is higher for larger creatures, and thus potentially more deadly. A creature such as a mouse falling at its terminal velocity is much more likely to survive impact with the ground than a human falling at its terminal velocity. A small animal such as a cricket impacting at its terminal velocity will probably be unharmed. This, combined with a relative ratio of limb cross-sectional area versus body mass, explains why very small animals can fall from a large height and not be harmed. Very low Reynolds numbers, Stokes drag. The equation for viscous resistance or linear drag is appropriate for objects or particles moving through a fluid at relatively slow speeds where there is no turbulence. Note that purely laminar flow only exists up to Re equals 0.1 under this definition. In this case, the force of drag is approximately proportional to velocity, but opposite in direction. The equation for viscous resistance is where is a constant that depends on the properties of the fluid and the dimensions of the object, and is the velocity of the object. When an object falls from rest, its velocity will be which asymptotically approaches the terminal velocity. For a given, heavier objects fall more quickly. For the special case of small spherical objects moving slowly through a viscous fluid, George Gabriel Stokes derived an expression for the drag constant. Where is the Stokes radius of the particle, and is the fluid viscosity? The resulting expression for the drag is known as Stokes drag. For example, consider a small sphere with radius equals 0.5 micrometer moving through water at a velocity of 10 aa micrometer s. Using 10^3 s as the dynamic viscosity of water in SI units, we find a drag force of 0.09 pn. This is about the drag force that a bacterium experiences as it swims through water. Drag in aerodynamics. Lift-induced drag. Lift-induced drag is drag which occurs as the result of the creation of lift on a three-dimensional lifting body, such as the wing or fuselage of an airplane. Induced drag consists of two primary components, including drag due to the creation of vortices and the presence of additional viscous drag. The vortices in the flow field, present in the wake of a lifting body, derive from the turbulent mixing of air of varying pressure on the upper and lower surfaces of the body, which is a necessary condition for the creation of lift. With other parameters remaining the same, as the lift generated by a body increases, so does the lift-induced drag. For an aircraft in flight, this means that as the angle of attack, and therefore the lift coefficient, increases to the point of stall, so does the lift-induced drag. At the onset of stall, Lift is abruptly decreased, as is lift-induced drag, but viscous pressure drag, a component of parasitic drag, increases due to the formation of turbulent unattached flow on the surface of the body. Parasitic drag. Parasitic drag is drag caused by moving a solid object through a fluid. Parasitic drag is made up of multiple components including viscous pressure drag, and drag due to surface roughness. Additionally, the presence of multiple bodies in relative proximity may incur so-called interference drag, which is sometimes described as a component of parasitic drag. In aviation, induced drag tends to be greater at lower speeds because a high angle of attack is required to maintain lift, creating more drag. However, as speed increases the induced drag becomes much less, but parasitic drag increases because the fluid is flowing more quickly around protruding objects, increasing friction or drag. At even higher speeds in the transonic, wave drag enters the picture. Each of these forms of drag changes in proportion to the others based on speed. The combined overall drag curve therefore shows a minimum at some airspeed. An aircraft flying at this speed will be at or close to its optimal efficiency. Pilots will use this speed to maximize endurance, or maximize gliding range in the event of an engine failure. Power curve in aviation. The interaction of parasitic and induced drag versus airspeed can be plotted as a characteristic curve, illustrated here. In aviation, this is often referred to as the power curve, and is important to pilots because it shows that, below a certain airspeed, maintaining airspeed counterintuitively requires more thrust as speed decreases, rather than less. The consequences of being behind the curve in flight are important and are taught as part of pilot training. At the subsonic airspeeds where the U-shape of this curve is significant, wave drag has not yet become a factor, and so it is not shown in the curve. Wave drag in transonic and supersonic flow. Wave drag is drag which is created by the presence of a body moving at high speed through a compressible fluid. In aerodynamics, wave drag consists of multiple components depending on the speed regime of the flight. In transonic flight, wave drag is the result of the formation of shock waves on the body, formed when areas of local supersonic flow are created. In practice, supersonic flow occurs on bodies traveling well below the speed of sound, as the local speed of air on a body increases when it accelerates over the body, in this case above Mach 1.0. However, full supersonic flow over the vehicle will not develop until well past Mach 1.0. Aircraft flying at transonic speed often incur wave drag through the normal course of operation. In transonic flight, wave drag is commonly referred to as transonic compressibility drag. Transonic compressibility drag increases significantly as the speed of flight increases towards Mach 1.0, dominating other forms of drag at these speeds. In supersonic flight, wave drag is the result of shock waves present on the body, typically oblique shock waves formed at the leading and trailing edges of the body. In highly supersonic flows, or in bodies with turning angles sufficiently large, unattached shock waves, or bow waves will instead form. Additionally, local areas of transonic flow behind the initial shock wave may occur at lower supersonic speeds, and can lead to the development of additional, smaller shock waves present on the surfaces of other lifting bodies, similar to those found in transonic flows. In supersonic flow regimes, wave drag is commonly separated into two components, supersonic lift-dependent wave drag and supersonic volume-dependent wave drag. The closed-form solution for the minimum wave drag of a body of revolution with a fixed length was found by Sears and Hook, and is known as the Sears-Hook distribution. Similarly, for a fixed volume, the shape for minimum wave drag is the von Karman ogive. Buseman's biplane is not, in principle, subject to wave drag at all when operated at its design speed, but is incapable of generating lift. Dalembert's paradox. In 1752 Dalembert proved that potential flow, the 18th-century state-of-the-art and viscid flow theory amenable to mathematical solutions, resulted in the prediction of zero drag. This was in contradiction with experimental evidence, and became known as Dalembert's paradox. In the 19th century the Naviero-Stokes equations for the description of viscous flow were developed by St. Venant, Navier and Stokes. Stokes derived the drag around a sphere at very low Reynolds numbers, the result of which is called Stokes' law. In the limit of high Reynolds numbers, the Navier-Euro-Stokes equations approach the inviscid Euler equations, of which the potential flow solutions considered by Dalembert are solutions. However, at high Reynolds numbers all experiments showed there is drag. Attempts to construct inviscid steady flow solutions to the Euler equations, other than the potential flow solutions, did not result in realistic results. The notion of boundary layers introduced by Prandtl in 1904, founded on both theory and experiment, explained the causes of drag at high Reynolds numbers. The boundary layer is the thin layer of fluid close to the object's boundary, where viscous effects remain important when the viscosity becomes very small. See also. Notes. References. French, A.P. Newtonian Mechanics, W. W. Norton and Company Incorporated, New York. ISBN A978-0-393-09958-4. Searway, Raymond A. Jewett, John W. Physics for Scientists and Engineers. Brooks Cole. ISBN A978-0-534-40842-8. Tipler, Paul. Physics for Scientists and Engineers, Mechanics, Oscillations and Waves, Thermodynamics. W. H. Freeman. ISBN A978-0-7167-0809-4. Huntley, H. E. Dimensional Analysis. Dover. LOC 67-17978. Batchelor, George. An Introduction to Fluid Dynamics. Cambridge Mathematical Library. Cambridge University Press. ISBN A978-0-521-66396-0. MREL 1744638. Clancy, L.J., Aerodynamics, Pittman Publishing Limited, London. ISBN 978-0-273-01120-0. External links, Educational Materials on Air Resistance, Aerodynamic Drag and its Effect on the Acceleration and Top Speed of a Vehicle. Vehicle Aerodynamic Drag Calculator based on drag coefficient, frontal area and speed. Smithsonian National Air and Space Museum's How Things Fly website.